Well, when we left off in our last part of the video, we saw a key fact was that the sample size and sampling error share this relationship, that the larger the sample size, the smaller the sampling error tends to be in estimating the population mean mu by a sample mean x bar. And the mean of the sample means we've found was equal to the actual population mean. That is, for samples of size n, the mean of the variable x bar equals the mean of the variable under consideration. And finally, we found this relationship was that the standard deviation of the sample mean, i.e. the standard error, for samples of size n, the standard deviation of the variable x bar equals the standard deviation of the variable under consideration divided by the square root of the sample size. And we use that fact to help us determine these characteristics of our samples and our sample distributions. Well, what realistic expectation could we get from this? Well, what happens if we don't have a normal distribution? For example, let's consider this histogram of a sample of 30 households. And we have a relative frequency of the household size itself. And in this diagram, we see that the number of people who are in a household, varying from 1 to 7, we find is a non-normal distribution. The highest distribution occurs at 2, the lowest distribution occurs at 7. It is clearly distributed in a very skewed fashion to the right. Well, if we were to take a lot of samples of size 30 and see what happened to their distributions, check out what happens. This histogram of the sample for 1,000 samples of 30 household sizes are superimposed using a normal curve. And when you look at that, the samples actually follow a normal distribution, which is very interesting. Our mean is actually at 2.5, and we can say that this is true for all distributions regardless of their type. As we increase the sample size, the sample mean, the distribution of our sample means always becomes normal. If we start with a normal curve and we start taking smaller and smaller, larger and larger sample size, we see that those samples approach a normal distribution. Well, of course, that would be true, but even if we took a very non-normal distribution, a reverse J-shaped distribution like this, for example, and started increasing the sample size, once again, we get an approximately normal distribution. Even for uniform distributions, once we start increasing our sample size, we start seeing that normal distribution. And it is an amazing fact of the Central Limit Theorem that this is always true. For sampling distributions of the sample mean for a normally distributed variable, we say the following. Suppose that a variable x of a population is normally distributed with a mean mu and a standard deviation sigma. Then for samples of size n, the variable x bar is also normally distributed and has a mean mu and a standard deviation, which is sigma divided by the square root of n. Let's use this as an example. When designing elevators, an obviously important consideration is the weight capacity. An Ohio college student died when he tried to escape from a dormitory elevator that was overloaded with 24 passengers. The elevator was rated for a capacity of 16 passengers with a total weight of 2,500. Well, let's check out the implications of what that would mean for us. Weights of adults are changing over time, and the table below shows the values of some recent parameters. For the following, we're going to assume a worst-case scenario in which all of the passengers are male. They obviously have a much higher mean weight for the population, and that could easily happen in a dormitory setting. If an elevator is loaded to a capacity of 2,500 with 16 males, the mean weight of the passengers is 156.25 pounds. Let me show you that here. If our population mean of males is 182.9, the standard deviation is 40.8 pounds. Our elevator capacity is 2,500 pounds. If you take 25 and divide by 16, you get 156.25. Well, what we're interested in is knowing is if an elevator is loaded to a capacity of 2,500 with 16 males, then the mean weight of 156.25 is our standard that we should expect. Well, let's first of all find the probability that one randomly selected adult male has a weight greater than 156.25. The population of male weights is normally distributed, and it has a standard deviation of 40.8 pounds. That is to say, let me get my pen out here, pardon me, that our normal weight for males is normally distributed with a mean of 182.9 and a mean of 40.8 pounds. Well, let's check the application of what this means. We want to find the probability that one randomly selected male has a weight greater than 156.25 pounds. I'm going to use Excel to help me do the calculation. So the probability that a male, a single male from the population, has a weight greater than 156.25 pounds, remember, is found by doing the following. We're going to take 1 minus, and we're going to use the norm.dist distribution. Now in that we enter x, which is our weight x, so we want 156.25 pounds. For our mean, we're using 182.9 pounds. For our standard deviation, 40.8 pounds. And of course we select true because we're using the cumulative distribution function to help us find this. Now remember this arrangement, we take 1 minus the normal distribution because whenever we get that normal distribution from Excel, we're getting the cumulative distribution of all of the weights less than 156.25. Since we want the probability that x is greater than 156.25, we take 1 minus that value. So our probability is 0.7432, right? 0.7432. So the illustration here in our normal distribution for x of males in the population of mean 182.9 and standard deviation 48.5 pounds, we find that there's a pretty high standard probability that a single male will have that weight greater than 156.25 pounds. What if we looked at a sample of 16 males, right? So let's take our sample of 16 randomly selected adult males that has a mean weight greater than 156.25. Basically what we're saying is that we want to make sure that if we get a sample of males, what is the probability that the average weight of those males in that group of 16 will have a weight greater than 156.25 pounds. The main thing to pay attention to in this scenario is that remember that our standard deviation changes. Because we are using a sample of size 16, we're going to have to take a mean of our standard deviation equal to the population standard deviation divided by the square root of n, which is 16. Well, let's go to Excel and help us figure this one out. So our sample standard error is going to equal the standard deviation of 40.8 divided by the square root of our sample size 16. Well, entering that in gives us 10.2, and so we're going to repeat the same calculation we did Except this time, this is the probability that our mean, population mean, our sample mean of 16, has a weight greater than 156.25. So we're going to put in equals 1 minus, and we're using the formula norm dot dist. And we're going to put in x, which is our 156.25 pounds. We're going to put in our population mean of 182.9 pounds. Only this time for our standard deviation, we're going to enter in that standard error of 10.2 pounds. And we're going to select true for the cumulative distribution function. 0.9955, which is a very high probability. In fact, we have a very high probability that the average weight of a group of 16 randomly selected males will weigh more than the desired average is 156.25 pounds. Message: if you look at the elevator capacity and you see 16 males coming towards that elevator, don't step on. Well, okay, so we have a very high probability that we're going to exceed our standard weight capacity with 16 randomly selected males getting on board that elevator if the capacity is 2,500 pounds. Well, statistically speaking, what do you think you'd be comfortable with? This is sort of an open question. I would ask you to respond, and you can respond by email or in your responses to this video. But think about what you would say would be with our capacity of 182.9, right? And what is the probability that the average weight is going to exceed that? And what way would you feel comfortable with getting on, assuming you're not claustrophobic automatically? All right, well, to wrap up, don't forget that the assignment's due this week by Friday of the 7th week. Make sure that you've watched the Chapter 7 lecture and completed the Chapter 7 lecture form. By Monday of week 8, make sure you complete the Chapter 4 web-assigned homework, and make sure you post to discussion board 4. That's all for now. Have a great week, everybody.